In this case study, we have exactly the same issue that we've had in our prior two case studies. Specifically, this PC cannot reach the host out on the internet with an IP address of 203.0.113.1. Let's confirm that. We like to begin our troubleshooting efforts by making sure we're interpreting the issue correctly. Can I ping 203.0.113.1? No, I cannot. It's not looking good. And again, on the real exam, we would probably do an IP config to see if we've obtained an IP address. And if we haven't, and we should have obtained an IP address from a DHCP server, we could start troubleshooting issues between the PC and the DHCP server. Here, though, I'm statically configured with an IP address. If I do a show IP interface brief, we can see that on this Cisco Catalyst switch, I'm configured with an IP address of 10.1.1.100. And a show IP route reveals my default gateway as 10.1.1.1. And I want to start following the path now. How far can I get as I go towards this destination on the internet before communications breaks down? Can I ping my default gateway? Can I ping 10.1.1.1? Yes, I can. And remember our strategy. We want to ping the ingress and the egress interface of every router hop, and that includes multi-layer switches, from the source to the destination. This is the IP address of the ingress interface on my default gateway, DSW1. Can I ping the egress interface on DSW1? Let's try to do a ping to 192.168.1.2. That was successful. Can I ping the ingress interface on R4? Yes, I can. Can I ping the egress interface on R4? It has an IP address of 172.16.1.2. No, I cannot. Interesting, isn't it? I'm able to get into R4, but I cannot communicate with the egress interface on R4. That tells me that I want to start my troubleshooting efforts on R4. Let's see what's going on there. Let's see if R4 knows how to get to this destination out on the internet. And if you look at the topology, something interesting about R4, you'll notice that it's an autonomous system boundary router. It has an interface participating in our EIGRP autonomous system, and it has another interface participating in OSPF. And the assumption is it's doing a mutual route redistribution between those two routing protocols. Let's see what routes are known to EIGRP. We can do a show IP EIGRP topology command. And I haven't learned very much via EIGRP. That's a bit of a concern. What about OSPF? I can do a show IP OSPF rib. And this will show me the networks learned by OSPF. And it does know about this 203.0.113.1 destination out on the internet. But that OSPF route has not been redistributed into EIGRP. Let's take a look at the redistribution configuration. Let's do a show run pipe to section router. And we see the configuration for both EIGRP and for OSPF. Under EIGRP, I'm saying redistribute OSPF process ID 1. And under OSPF, I'm saying redistribute EIGRP autonomous system 1. And I've given the subnets keyword to say don't just redistribute classful networks, redistribute subnets as well. And another way to look at routes known to OSPF is to do a show IP OSPF database command. And here we can see, for example, the network containing the PC. It was learned via a Type 5 LSA, which means that it came from outside our autonomous system. This is giving us evidence that we are redistributing EIGRP into OSPF, but it looks like we're not redistributing OSPF into EIGRP. Let's take a look at this configuration again. And you might want to pause the video and see if you can determine what's wrong with this configuration. For some reason, we don't appear to be redistributing OSPF into EIGRP, even though we're saying redistribute OSPF process ID 1, which is the correct process ID. Well, as you thought about this, did you remember that the default seed metric for EIGRP is infinity? When a route is redistributed into EIGRP, the metric is unreachable. Therefore, when we're redistributing into EIGRP, we need to specify a metric. Let's do that. Let's go into router configuration mode for EIGRP, autonomous system number 1, and let's reissue that redistribute command. Let's say redistribute OSPF 1, but let's add on to that a metric. I'm going to say metric, and we give the bandwidth in kilobits per second, and I'll say that I've got 10, 1000K of bandwidth. I'll say that my delay is 10 microseconds, and the unit of measure is tens of microseconds. So I'll just give a 1 there to indicate 10 microseconds. And I'll say that I am 100% reliable, I am minimally loaded, and I've got a default maximum transmission unit of 1500 bytes. Now that I've set that metric gets applied to OSPF routes that are being redistributed into EIGRP. Let's once again check our EIGRP topology table and see if it's any different. Let's do a show IP EIGRP topology. This looks much better, doesn't it? EIGRP knows about many more routes than it did previously, including this route that gets us to the internet host that was previously unreachable by the PC. Let's go back to the PC and see if it's resolved. Let's once again try to ping 203.0.113.1. This time it is successful. Fantastic. The issue we identified was a route redistribution issue. We needed to remember that the default seed metric for EIGRP was infinity, meaning that we needed to configure a metric for OSPF routes being redistributed into EIGRP. But one of the big things we want to take from this video is the strategy. Notice how quickly we isolated R4. We didn't spend time checking VLAN membership on ASW1. We didn't spend time checking a trunk configuration on DSW1. By doing a series of pings, we were able to very, very quickly isolate R4 as the prime troubleshooting target. Then we checked the routes known to EIGRP, we checked the routes known to OSPF, and it became evident that we were only doing redistribution from EIGRP into OSPF and not vice versa, and that led us to check the configuration and resolve the issue.